Hello everyone and welcome to another Würth Elektronik webinar. My name is Eleni Stark and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is derating for connectors. What do I have to consider? Our speaker is our Field Application Manager, Thomas Robock. He will hold today's webinar and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during this webinar today. This means that you can't ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us all your questions during the webinar at any time via our chat function. You'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within these 15 minutes, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at isis-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you fill out the survey and help us to improve our webinars. The link to the recording of today's webinar as well as the presentation will be sent to you in a separate email several days after the webinar. And you can also watch the recording of today's webinar a few days later on our website under the navigation point Webinars or on our Würth Elektronik YouTube channel. Now I will hand over to our speaker, Thomas Robock, and I wish you an exciting webinar.
Hello everybody and good afternoon from my side. My name is Thomas Robock and I'm working in the technical support for Würth Elektronics as field applications engineer. Today's topic for us is derating of connectors, and I would like to go through different steps and points with you to finally get a good picture of the whole derating issue or process. The first is, of course, we have to be aware what is the clear definition of derating, what does it mean to us. Then afterwards, we will have a look at the theoretical calculation in point of current, power, and of course, heat loss in this point. We will have a look at how a derating test has to be proceeded. So what is the requirement of the normatives? What tools do you need to proceed the test? Test equipment needed, all these kind of stuff. And finally, we will see what the rated current curve is and how we could adapt this rated current curve to create a derating curve, and how we have to work with this derating curve to get the final curve for the product, including all security and everything that is necessary. At the end of the webinar, we will have a look at some error images. So what can happen if you do not take into consideration the derating effect and the choice of your products. And we will have some design tips, well, where to look at if you have critical applications, what you maybe can optimize to have less problems with heat appearing. So let's start with the definition of the derating. The derating curve describes the maximum permissible power dissipation of an electrical or electronic component depending on the ambient temperature. So this means it's relevant for the use of the component in what ambient temperature you use it, because this reduces the current you're allowed to apply to the component. As you know, if you look into your data sheet of Würth Electronics, you have a given specified ampacity for a part, but this given ampacity is valid for normal room temperature. So you have to take care what is the real temperature when the part is in use. And derating literally means underloading. So we want to make sure with this derating curve that the affected component is really operated below its absolute maximum so that it cannot be defective in any way because of heat. We have some factors that influence derating. Thus, as the ambient temperature, like we already said. So this can be air, this can be some fluid, whatever, depends what is the surrounding area. I think for our applications, most of the time, it's simply the surrounding air. Then we have the maximum allowed self-heating of the component that is defined by UL or VDE, depending on the application you are in. So if I think, for example, on terminal blocks, there is a requirement from UL side that the self-heating that is allowed is maximum 30 Kelvin, and for VDE it's 45 Kelvin. This means even if the part is then not at its maximum temperature, but the self-heating area is done when you apply a certain current, you're not allowed to drive it with a higher current for security reasons in some applications. Then, of course, number of poles of the connector is a point that has influence on derating, because the more poles you have inside the housing, the more heat jam you can get in the housing, and so you have to lower the amount of current per pin to still be in an acceptable area. Then we have current and voltage specified on the datasheet. This is of course clear. You're not allowed to drive the part over specification. And then we have, of course, as a final part, the limiting temperature. For us in connectors, this is most of the time the plastics, because our plastics is most of the time in point of temperature the most sensitive part of the connector. And so when you're at the end of the area of the temperature area where you can use the plastic permanently, this is of course then the maximum temperature you can do in point of derating, otherwise you would damage the plastics. Additional influences on derating can be with mating cycles. So where? Because the connectors are specified for a certain amount of mating cycles, and after that, if you still mate and unmate them again and again, your contact resistance will increase, so you have more power loss as the resistance is increasing, so you create additional heat, which is not taken into consideration in the normal derating curve. This is measured during the normal specified mating cycles. And we have, of course, also the point of how to fix the part to the PCB. So this means we also have resistances between part and PCB, depends if we solder, if we press in the part on the PCB. In point of how we fix the cable, do we take care on the tightening torque to have the perfect contact resistance, or don't we take it too serious? So this all can create additional resistance and heat. And finally, the last point is, of course, you can, or sometimes you need to, take care on thermal management. Think about applications. You have a lot of current, but you have closed houses. So you have to take care about active cooling, or using some cooling parts, cooling bodies of aluminum to ensure that the heat inside the box can go out, not to drive your parts somewhere over the limit in point of temperature. For the theoretical calculation or point of view for the derating, it's necessary to have a look on the calculation of electrical power, which is of course the power is the square of the current multiplied by resistance. Quite easy and very basic. And the temperature rise in the component is directly proportional to the electrical power. So delta T is the temperature rise, and it's the square of the current multiplied by resistance multiplied by the specific constant for the material. And so you can see, of course, that the temperature rise is directly proportional to the resistance, but it's proportional to the square of the current. This is why in our curves we show the derating curve with current, and we do not apply the voltage here, because it's the main point here to take care of the current. The other point of the theoretical calculation is the heat energy in joule. So with the sign W, the formula here is R multiplied by square of I multiplied by T, where the small t here is time in seconds. So it's a heat energy over time. And this is an important point, because this is what drives a circle where you heat a system. More heat leads to problems with the resistance. It increases, it creates again more heat. And at one point, we have to take care that this cycle is not an ongoing loop, but we can stop it somewhere and stabilize the system. So the thermal energy is directly proportional to the transition resistance and time, and it's as well proportional to the square of the current. Very close to what we had before. So it's really important to ensure adequate ventilation and cooling of this system to break this loop of heating. To test the derating or to do the derating measurement, there is some requirements from DIN or EN normatives, and for the test of current carrying capacity. And it says that for the test, all contacts of the test specimen must be loaded at the same time with the specified current. So this is why you do a serial connection of all the contacts. Of course, it's also defined what size of wire you have to take for what current, and the wires are defined for 20 centimeters length. So for the basic measurement structure then, in point of how you make the temperature visible, you have two choices. Either you can measure the values and record it with thermocouples, or you can use a thermal camera. Depends on what is possible in the situation. The thermocouples normally, if you can apply them properly, give the more detailed information. For thermal camera, you have to take care that you paint the PCB where you measure black, what you want to make visible, to avoid any mirror effects that can lead to mismatches in your thermal camera image. Second, you need a power source and a meter to measure the ampacity, of course. And you could need a climatic chamber. It depends if you want to work at room temperature and have a stable room temperature. This is of course possible. If you want to measure at other temperature starting points, you need a climatic chamber, or if your room temperature is not stable. Here's just some pictures of the test devices. So the thermal camera on the left top picture, in the middle you see the image of the thermal camera. Left bottom side you have a power supply, and on the right side you have a thermocouple on the top, and 2 meters simply for measurement, for getting the values of the thermocouple. And here is a picture of a climate chamber to have stabilized environmental conditions. Here we can see on the left side thermocouples in practice. So this is a preparation for a measurement on fast-ons on the PCB side. So quite big wires, and the thermocouples directly mounted to the fast-on. The image on the right side with the 20 centimeter wires you've already seen before for the serial wiring. So now the requirement of the normative for proceeding the test. So the device on the test has to be put under load step by step with increasing current at the same ambient temperature, of course. And during the process, the temperature will be permanently measured and at defined points of measurement. And of course, we have to measure the temperature in the beginning before we start to have an initial temperature of our part. And as soon as we apply the first current, the temperature has to be measured at least every 5 minutes, better more often. And if the temperature rise is lower than 2 Kelvin during 3 measurements with 5 minutes in between each measurement, then we have to stabilize the whole system for 1 hour with that current to be sure that it has everywhere the same temperature and nothing happens anymore. Only after that we are allowed to go on with our measurement. So, and then we can proceed this again and again and again until the maximum temperature that we defined that is allowed for this part. And you have to do the whole process at least with 3 samples. So you can see it's a very time-consuming test to do a real good derating test according to the normatives for a connector. So it can easily cost you 3/4 of a day. And finally, we have now measured the current curve, the rated current curve, that we now have to transfer into the derating curve. And afterwards, we have to apply or to multiply the curve with 0.8 to have a security headroom of 20% to be sure that we do not get in trouble because of tolerances in measurement, tolerances in manufacturing of the parts, or these kind of things. Now, what you can see here is for a test here of one of our mini module connectors on the right side with a ribbon flat cable. We can see that we applied 3 thermocouples on this connector, one on the left, one on the right side, one in the middle. And on the diagram on the left side, you can then see why we did this, because the gray and the red line are the 2 thermocouples on left and right side. They are very close together, of course. This is how it should be. But the one in the middle is above. So in the middle, the temperature of the connector is higher because we load all contacts with the same current. It's serial. So we have a heat jam in the middle of the connector. And this is why it's important that we put a thermocouple at this, let's say, important spots where there could be an issue. The line at the bottom, the dotted black line at the bottom, is the thermocouple that this is the measurement of the ambient temperature to be able when it rises, because when we have enough heat in the climate chamber, this has influence, of course, on the temperature also inside. And we can correct then our measurement if we have the data how this temperature changed. We can measure, like we saw in the climatic chamber, for our rated current curve. We also could do a theoretical calculation if we have the correct basic load current, if we have some empirical values, and if you know the maximum load current. There is also a table existing on Excel how to calculate this for some connectors. So our field applications engineer have access to that, so you can get in contact with them if you need it for a certain connector to do some calculation. And out of this results, we can create this derating curve. If we compare the measured derating curve and the calculated derating curve, we can see a little bit of a difference, because here you see the measured curve. You see it's not 100%, let's say, straight. There is an unevenness, typical measurement. You measure every tolerance. In the calculated curve, it's a little bit different. The calculated curve is very smooth, very straight down, very in line. Of course, as there is no special tolerances of a certain part. This is also why it's very important to do the calculated curve on a very, let's say, traditional or level or safety respecting level. So if you overlay the curves, you can see that especially in the higher areas where it's getting critical, the calculated curve is lower than the measured curve, because of course you don't want to take the risk that because of tolerances of a part, something happens, something bad happens, just because you did a calculation. So you calculate some extra headroom in this area. For the next step, I would like to explain you how we come from the current capacity curve to the derating curve. So you can see here the current capacity curve of 3 testes that have been measured. And in the current capacity curve, we have a fixed ambient temperature, so our room temperature, for example. This is fixed, it's always the same. We apply current to the part and see how much current we can apply until we reach the temperature limit of the part itself. Okay, for the derating curve, it's a little bit different, because if you look on the x-axis here, we have current, in the current capacity curve. On the y-axis, we have temperature. Now, if we switch to the derating curve, we have the temperature on the x-axis and we have the current on the y-axis. And the thing is, we have the ambient temperature on the x-axis, not the part temperature anymore. Before, we had the part temperature in the curve. And how do we evaluate that? At first, of course, we have to know the temperature limit of the part, the upper temperature limit. This is, most of the time for us, the limit of the plastics. So 105, 125 degrees, sometimes 85, depending on the part. Now we take the delta of the derating curve to the Tmax line and we add it into that new chart. So with minimum 3 steps, better more. And this works like the following. For example, we took here the temperature 4 of the measurements of the rated current curve. And then we say we take the Tmax minus the delta from Tmax to the measured temperature at T4. So in this case, 69.85 degrees. And the current we applied at T4 measurement, we put here the temperature delta. And this is how we step by step get the derating curve. Now we just have to draw the line through all the points. Looks like this. So the higher the ambient temperature is, the less current we can apply. Now we are at the point where we have to compensate failures in measurement and tolerances. So now we apply the factor of 0.8 that I talked about before. And with that, we have the final derating curve. Now there's one more thing that can happen when you see a derating curve. And this is that you have a system exactly like you saw before with this red mini module connector on the ribbon flat cable. The mini module connector has quite big pins. They can carry a lot more current than the cable itself can carry. So the cable is limited to 2 amps. But as we specify the connector to be used with that cable, we have to adapt the derating curve for this connector to say, oh, this is limited to 2 amps because otherwise we have the risk to overload the cable. So, and you can see with the red line on the left side, we limit the derating curve to 2 amp from the beginning, even if the connector could do more because of the cable, and then we have the curve going down with higher temperature at the end. So in this case, this would be the final derating curve, how you can find it. Okay, that's how it works. And now it depends if you have to take care on the requirement in point of self-heating of UL or VDE. so self-heating of maximum 30K or 45K, you have to know where is your starting point. And in this case, this curve was measured at 20 degrees ambient temperature. So the maximum allowed to reach is 65 degrees for VDE. So 20 plus 45. And at that temperature, we are allowed to apply about 1.6 amp. So we cannot apply the full 2 amps to this part. Otherwise, we would have more self-heating that we would like. For VDE, it would be a little bit different, of course, as the delta that is allowed is different. Error images would be, well, melting plastics, decoloring plastics, material tiring. So if you take care on these effects of derating and what current you can apply, at what temperature, you could have issues with oxidation of contact surfaces, and this leads to less or a higher contact resistance, so not such a good contact quality anymore. So you create more heat, you have overheating. You can, in best case, you see it before you have decoloring, yellowing of plastics, but you can also lose mechanical properties if the plastic gets weak. Latches do not have the force anymore they should have, or they break easily because the plastic changes because of the temperature. Its behavior. It's getting more rigid. And in worst case, of course, insulation material can melt or burn, and you have a complete failure of your component or even the whole application. So this is really, really important to think about what the connector or where the connector will be used in reality in your application. So of course, if you have applications that do not require a lot of current and are operated in normal room temperature, the problem many times is not as big. But if you think about you're designing a street light, it can be in winter, it has -15, -20 degrees at night. In summer, it has +65 degrees in the housing, in the sunlight. So your connector has to carry all that. And of course, this is what limits then the current you can apply. And if you don't respect it well, you can really have issues with that. Here is an example with our MPC4 connectors. It's a 5-pin connector that is normally rated for 8 amps. And we put on that 25 amps just to show the effect. And it took about 10 minutes until it burned. And if you look at the diagrams, well, in the beginning, it was no big problem. It's at 37, 38 degrees, no problem, heat inside the connector. But at the end, it really went very fast until it went from, oh, it's hot now, I can still touch it, to it starts to melt and burn. So if you drive connectors to the limit, really take care and also explain this in the measurement of the derating, that you plan enough time to let the system run when you measure it, when you try to evaluate if it's stable, because this loop is getting faster and faster, and at the end of the loop, and if you just measure in the beginning, you can probably not see what will happen in 5-6 minutes. This can happen if you're not aware of the derating. This was a heater application with a high temperature in the housing. So of course you can imagine you can have 90 degrees in the housing, and the maximum temperature was 12 amps. The maximum current that was applied was 12 amps. Even if the specified current was 15 amps at 20 degrees, so room temperature, and the part is specified for up to 105 degrees. Of course, this was a lucky case because the plastic melted, but there was no open fire. But it could have been clear, because if you calculate the derating of the part, then you're allowed at 90 degrees to maximum apply 6.5 amps. So you nearly have the double here, or had the double here, and this is the result from overload at the end. So it's really important, just for finalizing the whole topic, that you take care on how to optimize your system to have the lowest heat dissipation you can have. So I know copper is expensive and big cables are not so easy to apply and so on, but if you want to avoid heat, take really care that your cable cross section is big enough, and better a little bit bigger than a little bit too small, because this cable is not only, it's not only that the cable itself gets hot, but if you bring it into a housing, it spreads the heat additionally into the housing, additional to the heat created by the other parts, and so it just drives this heat circle more and more, and helps that this heat circle starts. So it's also important to keep the cable in the housing as short as possible in the area where you get to the plug connection, to really try to keep the heat out of the housing as much as possible. And you have a bigger wire, a bigger cable, then it can also be that it can help you to cool down a little bit the system. If it's bigger, because outside the housing it's probably cooler. So you have to think about that there could also be a cooling effect by a bigger cable. Of course, the next point is something that's easy to say: dimension all components as large as possible. Bigger components can take more heat, but of course, due to requirements, we are bound sometimes also to certain housing formats and sizes, that we cannot easily take a bigger component. If you have the chance, it's good to do so, to choose the bigger component better than the small one if you really want to bring parts to the limit. Then, of course, depends on what connection you use. If it's crimp, rising cage clamp terminal, wire guard terminal, if you take care on tightening torques to do that. And also to rethink probably your ventilation system. How close and how small is your housing? Do you need active cooling? Is it okay if you can build some metal surfaces in the housing that can bring heat to the outside, like aluminum cooling bodies, things like that, to get some stable heat environment. And finally, of course, you can sometimes also optimize the connection to the PCB. So if soldering is probably having too much contact resistance and you create too much heat because you really need a lot of current, then you can also change to press fit solutions, for example, that have much lower contact resistance towards the PCB, and with that spread less heat. Yeah, that's it from my side for today, for showing up the issues or the effect of derating for you. So if you have any question, don't hesitate to contact us. And yeah, I will hand over to Eleni again.
And thank you very much, Thomas, for this great webinar. We will now get to your questions and have a look to all of them. You can now start also writing them into the chat board. In the meantime, I would also like to draw your attention once again to the fact that you will receive the presentation of this webinar a few days later in a separate email, and also in this email you will get the link to the recording of today's webinar so that you can watch everything once again, and also have the PDF file if you want to make your comments on. If you have any questions as well, just ask us and then you can have a look on it once again. So now we will try to have a look at the questions. So first question. There's one participant asking, my example refers to the MPC4, 16 pins with 2 pins with 8 ampere and 8 pins with 2 ampere. The rest is lower than 1 ampere. How should it be splitted?
Well, actually, to have a clear picture of what is happening there exactly, we would have to measure or clearly calculate it. But from the first impression, I would say, okay, take the 2 pins that have 8 amps and put them aside, left and right of the connector on the very outside, to be sure you have the biggest surface to the outside and the highest cooling effect. Then probably you have a row where you have the low current pins, and then you put the 2 amp pins, and in the middle again the low current pins, so that you have between the heat dissipation pins, I would call, yeah, the loaded pins, also some space so that you don't get heat jam inside the connector. This would be the best case in point of optimizing the temperature behavior of the connector.
So we got another question as well. If we use connectors like the ICS press fit, which are pure metal without plastic, why does the derating curve end at about 130 degrees Celsius?
Well, actually, I'm not 100% sure about the reasons for ICS, but as we also have press fit parts in our portfolio, and until short time ago, we also had the curves limited to 130 degrees. I think it's the same reason in the background. The point is that that most of the other parts on the PCB are already or are not specified for such high temperatures, so it was simply not necessary to bring these curves up to 150, 160 degrees at the end, because as you saw, the measurements take a lot of time and a lot of cost. So we limited them in point of temperature. Today, for our red cube products, we have all the curves up to 150 degrees.
There's another question which depends more or less to the same like we had before. It's automotive demands 150 degrees Celsius. Why are the curves always limited to 100 degrees Celsius?
Okay, yeah, this is of course also part of the previous answer. Well, for our connector portfolio, for example, we limit the curves because most of the time the plastic cannot go to 150 degrees. And for our connector portfolio, we are not dealing in the automotive branch, but we have an exception, which is our red cube portfolio. There we can go into certain projects in automotive. And this is also a reason why we have the curves there up to 150 degrees.
Okay, what do we have else? There's a comment from a participant. What I missed was a comment on the underloading of connectors. According to my understanding, they oxidize with time and lose contact.
Oh yeah, So I understand that you have been missing that, but I kept it out on purpose to avoid misunderstandings, because here we are really focusing on the derating. So in the underload of the part, in point of we don't want to bring it over the maximum of what it can do to have no negative impacts on the part. The topic in point of what you mean, I think you mean with underload, if I drive the part far below of what it can do. So if I have a part like a terminal block or whatever that can do several amps, and I drive it with some milli or microamps, then it's true you can have these effects because you don't have enough current load for a cleaning effect to burn off oxidation around the connection areas. But this would be honestly a different topic to go deeper into all these contact and oxidation effects when it goes to very, very low current.
Okay, I see that we have one last question. It's what kind of measurement method is best for temperature measurement if the contacts are fully enclosed by housing when engaged? Thermocouple or IR? And does thermocouple influences the measurement?
Well, in my experience is that if you can position the thermocouple in a good way without creating, let's say, two big holes where you have a lot of air circulation that can influence the measurement, or if you close the holes after you place the thermocouple, then this is for me the most precise way of doing that in my experience. With the thermal camera, it works. But you really have to take care what you use for painting the PCB black and so on. So it also depends on what kind of was heißt ein Laker you use to do that, how much reflection it creates and so on. And this problem you don't have with a thermocouple. So this is why, from my point of view and in my experience, it's, if you want to be exact, it's better to do it with a thermocouple.
Okay, so thank you very much, Thomas. We're done for now. We do not have any questions anymore. Thank you very much for your attention, for participating in once again in our webinar, and we hope to see you next time again. Bye-bye.